Preview.
A rise in temperature speeds up a reaction, where lowering a temperature slows a reaction down. At higher temperatures, motions of reactant particles are more chaotic than they are at lower temperatures. An increase in temperature causes a faster production rate. In this next video, we will show you a reaction being affected by temperature. Turn the hot plate on high, and then place 250 milliliters of water on the hot plate. Fill another beaker with 250 milliliters of ice water. Once the water came to a boil, we took the temperature of the hot water and then after the temperature of the cold water. The hot water was 90 degrees Celsius and the cold water was 15 degrees Celsius. We then placed a glow stick into each of the beakers. We allowed the glow sticks to sit in the beakers for 1 minute. After allowing the glow sticks to sit, we took them out, snapped them, and started the chemical reaction. The glow stick on the left was in the cold water, and the glow stick on the right was in the hot water. It is evident that the glow stick on the right is brighter than the one on the left. So remember, the greater the temperature, the faster the reaction. The lower the temperature, the slower the reaction. An increase in temperature equals a faster production rate. A catalyst is a substance which speeds up a reaction but is chemically unchanged at the end of the reaction. To increase the rate of reaction, you need to increase the number of successful collisions. One possible way of doing this is to provide an alternative way for the reaction to happen, which has a lower activation energy. A catalyst does not lower the activation energy of a reaction, however. If the particles collide with enough energy, they can still react in exactly the same way as if the catalyst was not there. It is simply that the majority of the particles will react via the easier catalyzed route. A catalyst provides an alternative route for the reaction with a lower activation energy. In this demo, we will be using 30 milliliters of 30% concentration of hydrogen peroxide, one squirt of sodium iodide, and a small amount of powdered soap. To begin, pour the 30 milliliters of hydrogen peroxide into the 250 milliliter beaker. Next, pour the powdered soap into the hydrogen peroxide. The hydrogen peroxide is constantly decomposing on its own. In order to speed up this reaction, we will add the sodium chloride, also known as the catalyst. As you can see, after we added the catalyst, the reaction occurred much faster.
Preview.
Remember, catalysts speed up a reaction without chemically changing the product. They provide an alternate route for the reaction. They speed up a reaction because they generally have a lower activation energy, and they do not lower the activation energy of the reaction. The smaller the particles, the faster the rate of reaction. There is more of a chance for particles to react. For example, imagine adding 10 grams of a powdered substance to a solution and then adding a 10-gram lump to the same solution. The powdered substance should react fully before the lump reacts fully. In this demo, we will be using granulated zinc,
Preview.
solid zinc, and 1 molar of hydrogen chloride. We will add a few lumps of the solid zinc into one of the beakers. And a small scoop of the granulated zinc into the other beaker. Then we will add half a bottle of the hydrogen chloride to each of the beakers. Then we will begin to stir. As you can see, the powdered zinc has already reacted much faster. It is still reacting, however, the solid zinc is bubbling much faster than the powdered zinc. Now remember, the smaller the particles, the faster the reaction rate. The bigger the particles, the slower the reaction rate. As the surface area increases, there is a higher chance of collision. The collision theory states that when suitable particles of the reactant hit with each other, only a percentage of the collisions cause any noticeable chemical change. These successful changes are called successful collisions. The successful collisions have enough energy, also known as activation energy, at the moment of impact to break the pre-existing bonds and form new bonds. This results in the products of the reaction. Using a catalyst or raising the temperature will bring about more collisions and will result in many more successful collisions, which increases the rate of reaction. When the oxygen collides with the hydrogens, adding energy will create water. The first part to an activation energy complex chart is the reactants. At this stage, the reactants have not yet reacted. In order to react, the reactants must achieve activation energy, the minimum amount of energy that is required for a chemical reaction to take place. The activation energy is much like a barrier that must be crossed in order to reach the products. The activation energy complex, which is the minimum amount of energy required for the bonds of a molecule to break apart and react. As the reaction is almost reaching the activation energy, the reaction will also reach the activated complex. This is where an unstable arrangement of atoms will form momentarily at the peak of the activation energy barrier. However, the activation complex will only form if the colliding particles have sufficient amount of energy and are oriented properly. The complex is extremely quick as it lasts for only 10 to 13 seconds. The last stage is where the reaction has been completed and the products are formed. When chemical reactions take place, they are often accompanied by heat changes. The system may give out heat to the surroundings, causing them to warm up. In this case, the reactants have more stored energy than the products. Such chemical reactions are exothermic. The system may take heat from the surroundings, causing them to cool down. In this case, the reactants have less stored energy than the products. Such chemical reactions are endothermic. Exothermics give out energy to the surroundings. Endothermic reactions take energy from the surroundings.